In this video, we'll discuss some basic rules of probabilities and some events that it'll be really useful to know how to deal with. We'll also discuss empirical and subjective probability. So the first probability rule we'll discuss is that the probability of any event should be between 0 and 1. Now it could be 0 and 1, so these are less than or equal to signs, but the probability is between 0 and 1. Now probabilities or proportions, that's another term for probability, when we get to calculated probabilities, can be written as percentages if we multiply them by 100. However, for the probability itself, the probability is a number that's less than 1. It's between 0 and 1 every time. So we can't have a negative chance of something happening, nor can we give 110% informal, boring math class probability. Probability rule 2. Probability rule 2 says if any event is impossible to happen, then the probability of that event is 0. So think about, this is like stupid duh impossible to happen, not like I'll never go out with you or something like that. This is like on rolling a single-sided die or a six-sided die, what's the probability of rolling a 9? Well, that's impossible. It's kind of a silly thing because it's just there's no possible way to do it. So probability rule 2 says with silly events that are just silly dumb, they're never going to happen, those events have a probability of 0. Now there's also silly dumb that it's going to happen every time. So consider a six-sided die. What's the probability of rolling something less than a 7? Well, if I've got 1 through 6, yeah, duh, it's always going to be less than 7. Now those events, if it's certain to happen, if it's going to happen every single time, the probability of that event is a 1. Now the fourth probability rule seems kind of weird. It says that the sum of all of the events in the sample space of their probabilities is 1. So if I look at all the events in the sample space and add all of their probabilities up, those are going to add up to 1. Now this is a really useful feature. We'll talk about this in just a second, but it's something that may not strike you as particularly useful. So we'll have an example of this real quick, and then we'll talk about why this is so useful. So consider a six-sided die and think about the probability for all of the events in the sample space. So the sample space is 1, 2, 3, 4, 5, 6. Well, what's the probability of each of these? Well, the probability of rolling a 1 on a die is 1/6. The probability of rolling a 2 on a die is also 1/6, and so on. So the probability of each of these events happening on the die is 1/6 for each. Now what probability rule 4 says is if we add up all of the probabilities of every event in the sample space, then if we add all of them up, that sum should be 1. So we add up all of these different probabilities, and indeed, if I add 1/6 plus 1/6 plus 1/6 all the way out 6 times, then 6 times 1/6 is 1. And if you don't trust me, type it into your calculator and you can check it. All right, now why is this so gal darn useful? It's so useful because of something from set theory that actually carries over to statistics and probability, and this idea is complementary events. It's not saying you look great today, it's the complement, which actually means the opposite. Not the opposite. It's not like a rude event. It means the opposite of the event. That's what complementary events are, the opposite. So consider the sample space for the roll of a die, 1, 2, 3, 4, 5, 6, okay, duh. The event of getting an odd number is 1, 3, or 5. So the opposite of getting a 1, 3, or 5, or the opposite of getting an odd number, is an even number. That would be a 2, 4, or 6. So the complement of event E, which is odd numbers in this case, is even numbers. Again, complement meaning opposite. Now, in notation, this is from set theory and probability, the complement is the event with a little bar over it. Now, this gets confusing, and again, this is where I mentioned in the last video, you kind of have to separate the notation for a probability from what we've been doing thus far in statistics, because this E bar does not mean the sample mean of E. This means the opposite of E, or the complement of event E. So don't get it confused with the average. I know it's annoying. Just bear with me. It'll be over soon. But for all of our probability stuff, when you read E with a little bar over it, just remember that is the opposite of event E. So let's practice a couple. So what is the opposite of rolling a die and getting a 4? Just pause your screen, write out the event space for the complement of event E. All right, so E is just the number 4. The opposite of event E is 1, 2, 3, 5, 6. Everything except for the number 4 in there. All right, so selecting the letter of the alphabet and getting a vowel, what would the complement be? You can pause and give it a shot quickly. All right, so the complement, here are the vowels. The complement is going to be the consonants, or everything that's not A, E, I, O, U, or I guess sometimes Y if you want to throw that in there. What is the complement of selecting a month that begins with the letter J? Pause it and give it a shot. Well, complement is everything that isn't that. So J is January, June, July. Complement is all of the months that aren't January, June, or July. Last one, complement of selecting a day of the week and getting a weekday. Well, if you get a weekday, that's Monday, Tuesday, Wednesday, Thursday, Friday, the complement or the opposite of that is a weekend, Saturday and Sunday. There's a few rules that go with complementary events. So if you think about this, selecting a day of the week and getting a weekday, Monday, Tuesday, Wednesday, Thursday, Friday, plus Saturday and Sunday. So if we look at E plus E bar, or the complement of E, we end up getting all the days of the week. E, January, June, July, plus E bar, all of the months that don't have a J. If we add these together, that's all the months. If we add the vowels together plus the continents, or the continents, oh my gosh, it's been a long day, team, plus the consonants, that would be all of the letters. If we add 4 plus all the rest of the numbers, that's all the numbers on the die. So our rules for complementary events are going to come from the fact of this last one, actually, that if we combine the event E plus the complement of the event E, that's the entire sample space. So if we look at the probability of the entire sample space, that's just 1. It's certain to happen. So the probability of event E plus the probability of the complement event E is 1. And actually from this, we can calculate these top two. We just subtract one of these or the other from the other side. So if I want the probability of event E, I just subtract probability of complement of E from both sides, and I get 1 minus probability of the complement of E. If I want the probability of the complement of E, I just subtract the probability of E from both sides, and I get probability of the complement of E is 1 minus the probability of event E. Now, Venn diagrams can be very useful in displaying these, but this is really, really cool because sometimes, actually later in the course, we'll address this directly, there are events that are really difficult to calculate, but their complement is really easy to calculate. So if I'm looking for the probability of a really, really difficult event, I'm going to come back to this equation if the complement is easy to calculate. It's not always straightforward when this is the case. It can always be the case. You just kind of have to keep your eye out for it. But if the event's hard to calculate and the complement is easy to calculate, I can use this formula to make my life a whole lot easier in terms of calculating the probability of an event. Incidentally, that question on the exam is the most missed question on the exam. Just saying. All right, moving on from classical probability to empirical probability. Complements happen in both, but typically in classical because classical uses sample spaces. Empirical probability, again, is very different from classical probability because it doesn't assume that all events are equally likely to occur. It uses data to list the probabilities of events after observation. So this empirical is show me the data. That's what the empirical probability is all about. So we use the frequency of how often something happened, and we're going to have different classes of observations. So you rolled a 1 on a die. How often did you do that? You rolled a 2 on a die. How often did you do that? So the frequency for each of the possible options divided by the total number of tries that we had. This is called empirical probability because it's based on empirical observation. So for example, let's look at the distribution of blood types. Now in classical probability, we would find the sample space A, B, AB, O, 4 different blood types, and we would assume, recall the big assumption in classical probability is that they are all equally likely. We would assume that there's a 25% chance of getting each. However, with empirical probability, we don't have to do that. We just have to go collect data and see how often each of these events occur. So in this, we collected a sample of 50 people and we recorded their blood type and we made a frequency table. This is from back in chapter 2, where we call the frequency table. The empirical probability says that a person who has type O blood, so that this is type O, we had 21 individuals, is the number of people who were in this class divided by the total number of observations. So that is, we had 21 people who had type O, and then we had 50 total people. The probability of type O blood from empirical probability, the show me the data probability, or the data collection style of probability, is to use our 21 individuals divided by the 50 total individuals and say we have 21 out of 50 chance of having O blood. Let's do a couple more based on this distribution. Just pause the video, give it a shot on your own. What's the probability that a person has type A or type B blood? Pause it and give it a shot. Okay, so type A, 22, type B, 5. You can have either one, so there's 27 possibilities. 27 people had type A or type B blood out of 50 total, so our probability is 27 out of 50. What is the probability that a person does not have type AB blood? Pause it and give it a shot. Now there's two ways to look at this. You can either say, well, AB blood is this one, not AB is O plus B plus A. I'd have to do all three of those. Or you can look at this using the complement that we looked at last time. The probability of the opposite of AB, this is like E bar, is 1 minus the probability of having AB. So the probability of having AB is 2 divided by 50, and 1 minus 2 divided by 50 is 48 divided by 50. So this is using our complementary events rule. Note that you could also do A plus B plus O, 22 plus 5 plus 21, also gives you 48. So you can approach this from two different directions. You save a bit of work maybe doing it this way. This is not the amount of work I'm talking about saving. We'll, again, at the end of this chapter, deal with much, much, much more difficult probabilities that complementary events can do. This is a very, very simple example that you could have used a complementary event on. All right, let's try another example. So hospital stays for maternity patients. So we're going to take a sample of 127 maternity patients, and we're going to look at the number of days that they were in the hospital and how often that happened. So first, pause the video, find the empirical probability that a patient stayed exactly 5 days. Well, how often did the 5 days happen? Well, it happened 56 times. How many total patients do we have? 127 patients. So our empirical probability is going to be 56 divided by 127. All right, now go back to the previous table. Find the empirical probability a patient stayed less than 6 days. Pause it and give it a shot. Okay, so less than 6 days. Here's 6. 6 doesn't count, it's just less than. So 3, 4, or 5 are less than 6 days. So we've got 15, 32, 56. Add all those up to get 103. Divided by 27, the probability of less than 6 days is 103 divided by 127, our empirical probability. Find the probability that a patient stayed at most 4 days. Now this is the probability of being less than or equal to 4. So give this one a shot. All right, coming back, probability less than or equal to 4 is 3 or 4, so that's 15 plus 32, gives us 47 out of 127. That's the probability, empirical probability of being less than 4. All right, Final one, find the empirical probability that a patient stayed at least 5 days. So 5 days, we have 5, 6, or 7. At least 5 days. That means that the lowest number of days can be 5, but we could have 6 or 7, both as possibilities. So we have 56 plus 19. 56 is the number of patients who stayed 5 days. 19 stayed 6 days. 5 stayed 7 days from our previous table. We have a total number of 80 patients. That gives us out of 127. So this is our empirical probability, 80 divided by 127. All right. So as we consider empirical and classical probability, the law of large numbers is an important thing to know about. Said very, very simply, the law of large numbers says that as your sample size gets larger and larger, the empirical probability approaches the classical probability. So let's say I gave you a fair coin and asked you to go flip it. And I'm going to do classical probability and say there's a 50% chance you get heads. But then you actually flip the coin and it was tails. On a single coin flip, you would determine empirically, well, I had one coin flip, so that's my total number of trials, and I had one not heads, so 0 heads, so the probability of getting a heads is 0 out of 1. That's 0% chance of getting a heads. And maybe even if you flip it twice, it's absolutely possible that if you flip a coin twice, both times are not heads. So even if you flipped a coin twice, then you might get 2 not heads. But what the law of large numbers says is as you flip the coin 10 times, well, you might have 6 heads, you might have 4 heads, but it's very unlikely you would have 0 heads. As you flip the coin 20 times, you're probably going to get around, but maybe not exactly 10 heads. And then as you flip it 100 times, 1,000 times, 1,000,000 times, if you flip your coin more and more and more, the empirical probability is going to get closer and closer and closer to the classical probability if the assumption of the classical probability is true. That is, if each option in the sample space is equally likely. This phenomenon is known as the law of large numbers. All right. Now we've talked about classical and we've talked about empirical, but I mentioned we were going to talk about subjective probability. Many people don't like subjective probability, let's be honest. Subjective probability uses the knowledge of the relevant circumstances to make a probabilistic claim. The problem is that it's very subjective. It's not necessarily bad, though. It just really, really, really depends on how good the person is who you asked to make a subjective probability. Sometimes, actually, subjective probabilities can be really good. They can be better than stuff that we can come up with theoretically. If the person really knows what they're talking about and if there's a lot of difficulty in approaching a classical or an empirical probability. However, it's not particularly reliable. Of these methods, subjective probability is probably the least reliable method, and it's just because it is so variable depending on the person you ask, and so much depends on asking that question. One final idea that we'll briefly discuss is the topic of odds. Odds are another expression of likelihood. So we have probability. There, you can also express likelihood in terms of odds. The calculation for odds, instead of the size of the event space divided by the size of the sample space, is the size of the event space divided by the size of the complement of the event space. Or we could say the number of successes divided by the number of failures. So we roll a die, say, I bet you $50 it's an odd. Well, the probability would be the size of the event space, 3, there are 3 odd numbers, divided by the size of the sample space, 6. The odds would be how many different ways could Dr. Florin win versus how many ways could he lose. So there are 3 ways I can win in the odds, and there are 3 ways I can lose, namely if it's in one of the 3 even numbers. So the odds in that particular case would be 1. It would be 3 divided by 3, which is 1. This make odds really difficult to interpret. Now, they are useful in a variety of settings. I write money transfers on here. I'm talking about gambling. They're useful in gambling. But when we're dealing with them and trying to interpret them, many people, in fact, I'll even go so far as to say the majority of people, most people, interpret odds as probabilities. And that is very, very bad to do. As opposed to spending several weeks talking about odds and just beating it into your head how to interpret them appropriately, what I'll recommend, because odds can be turned into probabilities, is that you turn odds into probabilities if you're working with them, or you're just really, really, really careful when interpreting them. So yeah, there's some issues with it. I mostly have this slide in here to give you a warning on be very, very, very careful when working with odds. They are successes divided by failures instead of successes divided by the total number of potential options, or the size of the event space divided by the size of the complement of the event space instead of the size of the event space divided by the size of the sample space. Again, these are just, they're irritatingly pervasive and so commonly misunderstood and misinterpreted that frankly, I don't even want to touch on them in this class. If you do have questions on them, please let me know. But otherwise, like, you're not going to have any exam questions on them. Maybe you'll have a question on why does Dr. Florin hate odds? And the reason is because they're so difficult to work with. And actually the biggest reason is because very few people can accurately interpret them. It's not that they're difficult. It's just that most people tend to want to interpret them like probabilities. And in that case, you should just calculate a probability anyway. So for example, the odds of getting a heads on a fair coin flip are 1 to 1, or 1 divided by 1, or 1. So the odds of getting a heads are 1 as opposed to 0.5. And this is really hard for people to wrap their minds around. So again, we just kind of breeze over this. We finished up our conversation on sample spaces and probability, talking about empirical probability, the probability rules, and subjective probability, and odds with the law of large numbers we talked about just a bit ago. In the next video, we'll move on to talking about the addition rules involved with probabilistic calculation.